Hi, this is Barrett Givens, and in this example, I want to show how we can prove that a function is not continuous using the topological definition of continuity. So here's a function. We're going to let f of x be 1 if x is greater than or equal to 0, and -1 if x is less than 0. And I want to show that f from the reals to the reals is not continuous. And when I just say the reals like that, reminder, that means the reals with the standard basic open interval topology. All right. To show a function is continuous, you have to think about arbitrary open sets and show that the inverse image of any open set is open. To show it's not continuous, you just have to find an example of an open set whose pre-image is not open. So we just kind of have to play around a little bit with some examples of open sets whose pre-image might not be open. And remember, I've drawn over here a graph of the function. And when we look at a graph like this, we always think of the horizontal axis as the domain and the vertical axis as the codomain. So I want to think about open sets in the codomain. I want to think about open sets on the vertical axis. And probably I want to think about basic open sets on the vertical axis. So like a basic open set could be like an open interval like that, or it could be an open interval that just has 1 in it, or it could be an open interval that just has -1 in it, or it could be, all kinds of things. But given that I can see with my eyeballs that it looks like the point of discontinuity is happening there when you jump from 1 to -1, I want to think about open sets that contain either 1 or -1 or both. Maybe, I don't know, I might have to play around with it a little bit. Okay, let's just like try a couple of examples. Maybe I just want to try something like f inverse of the open interval from -2 to 0, or f inverse of the open interval from 0 to 2. I'm just picking some open intervals that happen to contain the points 1 and -1. Let's compute both of those and see what we get, okay? So the inverse image of the open interval from -2 to 0, that would be this set here. So I want to know which inputs correspond to those outputs. So the outputs that correspond to that whole line is just this part of the graph. And so this is the possible inputs that lead to that output are just -infinity to 0. Now, is 0 included in that or not? If I look at f of 0 from the definition, f of 0 equals 1. So f of 0 is not between -2 and 0. So this should not include 0 here. Okay. Now let's look at the interval from 0 to 2. Let's look at the interval from 0 to 2. So that's this bit right here up above. The parts of the graph that land inside that, the parts of the graph that correspond to that, is this part to the right over here. That corresponds in the domain axis, in the horizontal axis, that corresponds to 0 to infinity. Do I include 0 or do I not include 0? I do include 0 because when x equals 0, I do land inside that interval. So I get that. Okay. Now I claim that one of these two statements helps me show that f is not continuous. To show that f is not continuous, I just need an example of a basic open interval whose pre-image is not open. So that would be the second one here. Since 0, 2 is open, and f inverse of 0, 2 is the closed interval from 0 to infinity, is not open, f is not continuous. All right. So the first example that I did from -2 to 0, it turned out that didn't help me. So you might want to do that on scratch paper and not include it as part of a write-up for a problem like this. So you would just, you would just say, well, that didn't actually help me. Okay. It helps you because it helps you understand what's going on, but it's not going to be part of the solution to this problem. All right, now let's vary this problem a little bit. What if I keep the same function, but I'm going to change the domain to R with the lower limit topology, R with the lower limit topology. And recall that the lower limit topology is the topology where basic open sets have the form of intervals a comma b, where a is included and b is excluded. So those are the basic open sets. Okay, so the domain has the lower limit topology. The codomain still just has the standard topology. And I claim that this function is continuous in this case. This function is continuous in this case. So let's think about why. First of all, I can't just give an example now. I have to think about all possible open sets in my codomain. And I think that means I'm going to have to think about some cases. Okay. Um, so let's see if we can do this. Proof. Consider, I don't have to think about all possible open sets. I can think about basic open sets, which helps a lot. Okay. Consider a basic open set A comma B in R, which is the codomain. Okay, so I start with a basic open set in the codomain, which is R in this case, with the standard topology. Now, when I think about F inverse of this, I'm going to have different answers depending upon where A and B lie compared to 1 and -1. So I think I'm going to just write like a big sort of thing by cases here. F inverse of A comma B equals, and let's just think about all the possibilities. So one possibility is that A and B are both above 1. So then if I take an inverse image of something that's way up here, there's no part of the graph that corresponds to that. So that is empty set if 1 is less than or equal to A, which is less than B. The next case is, let's say that I actually go down far enough that 1 is included. Then I would have 0 to infinity if -1 is less than A, less than or equal to A, actually, which is less than 1, which is less than B. Actually, you know what? I'm going to make this a little bit easier on myself. I've changed my mind about how to do these cases. Let's say it's empty set if 1 and -1 are not in AB. It's 0 to infinity with 0 included if 1 is in AB, but -1 is not in AB. It will be negative infinity to 0, not including 0, if 1 is not in AB, but -1 is in AB. And then finally, it's all reals if 1 and -1 are both in AB. Okay, so I listed out the 4 possibilities for whether or not 1 and -1 are either in or out of this basic open set. It actually didn't even need to be in basic open set here. I could have just written it as a capital U. The fact that it's an interval doesn't really change anything in this case. So I could have just said capital U everywhere here. I think that's a little nicer, actually. Okay. So, all right. So if I look at the inverse image of a basic open set U, it's either the empty set, which is open, the set from 0 to infinity, including 0, which is open in the lower limit topology, the set from -infinity to 0, which is also open in the lower limit topology, and the set of all reals, which is also open in the lower limit topology. So in all cases, F inverse of U is open in R with the lower limit topology. So F is continuous. Okay. What is the point of these two examples? The point of these two examples is that when I ask you if a function is continuous, it depends not just on the function, but on the spaces that the function has as its domain and codomain. Certainly, this function does not look continuous to us because we have an intuitive understanding of continuity from algebra, calculus, real analysis. And when you're going from the reals to the reals with the standard topology, which is what all of us, sort of grew up with and know and love very well, this is not a continuous function. But if you use a different topology, such as the lower limit topology, when I change it to have the lower limit topology on its domain, it suddenly becomes continuous. Okay, it becomes continuous. And in fact, if it went from the lower limit topology to the lower limit topology, I think the same argument would still work. But the point is just that you can't necessarily look at a picture and know if a function is continuous. You really have to think about the definition that the pre-image of open sets is open, and you have to think about what the meaning of open is in the particular topology that you happen to be given. So whether or not a function is continuous depends not just on the function, but also on the topology given for the function's domain and codomain. All right. Thank you for listening.